We're going to look at matrix multiplication. I have a couple of matrices up here that we are going to look at multiplying. I have a 2 by 3 and a 3 by 3 matrix here, so a non-square and a square matrix here. One of the things that we need to do when looking at multiplying matrices is to check dimensions. Like addition or subtraction of matrices, only certain dimensions of matrices can be operated on. And this is going to work a little bit differently than it does for addition and subtraction. I'm going to make a notation of our dimensions here. Notice we have 2 by 3. And this one is 3 by 3. So we have 2 by 3 and 3 by 3. The thing that we need to check is we need to look at, when we write them down side by side, the two numbers that are closest together. In other words, the number of columns in the first one has to match the number of rows in the second one. And it will soon be kind of apparent why that is. Once we see that those inners match, the outer two is going to be the dimensions of our product, our result when we multiply the two together. So I have 2 and 3 here. So I'm going to have a matrix that is 2 by 3. It's going to have 2 rows and 3 columns. When you're first starting out learning how to multiply, you may want to put little blanks in here so that you make sure that you fill in all the blanks so that you know that you are done with your multiplication when you have all of those blanks filled in. There's a lot of side work to do when multiplying these matrices. Essentially, we are going to take the top row from the matrix, stand it upright, and multiply it successively across the columns of the second matrix. And then we're going to do the same thing with the next successive row, stand it upright, and multiply it across. Let's take a look at what happens. We're going to take the 3, 5, 0 here, and I'm going to write them underneath here, and this is just side work that you do. I'm going to write them vertically here. And then I'm going to write the 1, 7, and 5, which is the first column here. So I have 3 times 1, 5 times 7, and 0 times 5. So I'm going to do these products. 3 times 1 is 3. 5 times 7 is 35, 0 times 5 is 0. Once I have this column of products, I'm going to add those together. So I have 38 as my total. That will be the first blank that I fill in here. So I have done 4 separate calculations to get this one term. I've multiplied 3 times and then I've added once. You will have to do that until all of these blanks are filled up. Again, what I'm going to do is I'm going to take this top row and stand it upright. So I have 3, 5, 0. And then I'm going to take the second column here and write that beside of it. And I'm going to multiply each of these and then add those products up. 3 times 2 is 6, 5 times 5 is 25, 0 times 0 is 0. I'm adding these up. So I have 31. That's going to be my next number in this product matrix. Lastly, I am taking this row, standing it upright, and multiplying by the last column here. So I have 3, 5, 0, 1, 4, 3, multiplying again, 3, 20, and 0. Adding those together, I have 23. That goes in the last blank on the top row. So I have my top row filled in now on my product. And we are going to look at filling in the next row now. I'm taking the second row now, standing it upright. And I'm going to multiply it by, again, the first column. So 2 times 1 is 2, 1 times 7 is 7, 7 times 5 is 35, and then I'm going to add these up again. 42, 44. That's going to be the first entry in my second row in my product. Taking the second row, standing it upright, multiplying by the second column here. 2 times 2 is 4, 5 times 1 is 5, 7 times 0 is 0. I have 9 here for a total. Last row, last column, 2 times 1 is 2, 4 times 1 is 4, 7 times 3 is 21. I'm going to add those together and get 27. This will go in my last spot here, so I have this as my final product. I took a 2 by 3, multiplied by a 3 by 3, and I got a 2 by 3 as my final product. Let's note a few things about what is happening here with matrices. Notice we had to have a specific set of dimensions on our matrices to be able to multiply them. Let's label this one A and this one B. So I multiplied A times B, and we'll call this result C. I got C. If I commute these and I do B times A, notice I will have the B is 3 by 3, the A is 2 by 3. The inner dimensions don't match, and so we're going to have to say that this is undefined. This is an important observation for matrices, namely that the commutative property does not hold for matrices. So that is something to note. We have no commutative property for multiplication when we're dealing with matrices. It works for addition, we can commute those will work, but there's no commutative property for multiplication. This means that there is a specific order that you have to multiply in, and you can't change that order. Associative property will work. If you have 3 matrices to multiply together, you can choose which 2 you multiply together first. You could do AB and then C, or BC then A, but you have to essentially multiply those in the order that they are occurring from left to right. This will also mean that a distributive property idea is going to be different. What it gives us actually is 2 distributive properties. If we have B plus C in parentheses and matrix A on the outside, this is going to mean that we have matrix A times matrix B plus matrix A times matrix C. If, on the other hand, we would have had B plus C in parentheses, but A was on the right-hand side, this distributive property means that we have B times A plus C times A. We have a left-hand and right-hand distributive property for matrices. We're not used to that when we're used to the real numbers. These distributive properties are only talking about a matrix times a set of matrices in the parentheses separated by a plus or minus. This is not talking about scalars, which is just a number multiplied by a matrix. That will work with distribution from both sides without a problem. Let's take a look at another one of these problems. Look at this problem. I have a 2 by 2, a 2 by 2 matrix. 2, 3, 5, 7, and 3, 1, 4, 2 in these matrices. Take a minute, try it, possibly pause the video, and then I'm going to walk through this problem. Let's take a look at this problem. It's going to work the same way that it did before. I've just used a couple of smaller matrices, so this will hopefully go a little quicker. The first thing that I'm going to do is I'm going to do a dimension check. I have a 2 by 2 here, and I have a 2 by 2 here. The two inner numbers match, so the two outer numbers are going to be the product. So 2 by 2 again. This leads to an idea that if we take a square matrix and multiply by a square matrix, we will get a square matrix as the result. We still can't commute these. We get a different result. I'm going to take the top row here, turn it sideways, so I have 2 and 3, and I'm going to multiply by the first column here, which is 3, 4. 2 times 3 is 6, 3 times 4 is 12, and I'm going to add those together. So 18 is going in my first position. Now we're going to erase some of this. Again, taking the top row, turn it sideways, I have 2, 3. My second column is 1, 2. 2 times 1 is 2. 3 times 2 is 6. We're going to add those together, and I have 8 for my second number. Now we're going to take the second row, turn it upright, so I have 5, 7, and multiplying by the first column, I have 3, 4. 5 times 3 is 15. 7 times 4 is 28. We're going to add these together. 5 plus 8 is 13. 2 plus 1 is 3. Carry the 1 is 43. And then our last set of calculations. Then I have my second column here. 1, 2. We're going to multiply those together. I have 5 times 1 is 5. 7 times 2 is 14. Adding those together, I have 19. So my product is 18, 8, 43, 19. Real quickly, what I want to do now is I want to reverse the order just to demonstrate that we can't commute these, even though things look a lot nicer with these square matrices. I'm going to switch these positions. And now I want to run through this calculation. I'm going to commute these, multiply, and then we want to compare the two product matrices here. This is going to be a 2 by 2 again. We have 2 by 2. Our inner dimensions show us 2. Our outer dimensions are 2 by 2. My first row here is 3, 1. My first column is 2, 5. I have 6 plus 5 here, which is 11 for my first position. And I don't need to go any further. We can already see that 18 and 11 are not equal to each other, so these are not going to be the same product. We would have 16 for the second position here, 18 for the third, 12 and 14. I think this is our second matrix here. We have 11, 16, 18, 26. Notice that there's no distinguishable pattern between the two of these. We get an 18 in both matrices, but in different positions. Nothing else really matches. Hopefully this is helpful in understanding some of the basics of multiplying matrices together. Cheerful Calculations.